Hello everyone. This video is about the teaching of algebra across the grades, otherwise known as algebraic thinking. And in this video, we're going to explore the question, well, what is algebraic thinking and what are some key concepts that should be developed across the elementary grades to kind of build this type of thinking in our students? So to begin, why not begin with a little warm-up here? So if you want to pause your video for a second and figure out the red question mark at the bottom. All right, good. How about one more? Take a look at this one for a second. Go ahead and pause the video and see if you can figure out the value of the spacecraft at the bottom. Well, good. Well, these puzzles are just one example of a type of algebraic thinking that we see at play here. Obviously, in these puzzles, we see some interesting use of variables that stand for a constant number, and we see some relationships between numbers to think about to go through here. But let's unpack this a bit more. When we look at the Common Core standards and the different domains that are focused on grade level bands, we see across K-5 in the blue one that's called operations and algebraic thinking. So in the Common Core standards themselves, there are sets of standards at each grade level, K through 5, that do address certain aspects of algebraic thinking. Obviously, if this topic is important enough to make it into a title of a Common Core domain, it's good to unpack it a bit and think more about what that actually means. So in the last few weeks, I believe that you had a chance to reflect on this question after doing some reading in our course text about an interview question where you're asked to, kind of in your own words, explain what algebraic thinking was and give some examples. And you may recall doing that now. Well, one thing you may have realized in reading the book is there's not one clear, concise definition of maybe what algebraic thinking is. And when you looked at the examples in the text, it did seem to cover quite a variety of things, which is true. And so let's take a look a little deeper at what some of those key components are that comprise algebraic thinking. One definition I really like comes from a past president of NCTM named Kathy Seeley. And in some of her writings, she said that algebraic thinking includes things such as recognizing and analyzing patterns, studying and representing relationships, which at the bottom there shows that really can focus on variables, kind of meaningful use of symbols, solving for unknowns. She also said making generalizations and analyzing how things change. So interesting. Within that definition, and when you think back to your writing for the reflection, there's some key words that I would recommend that you focus on that would be included in your response to such an interview question. And those type of words are the use of patterns, different types of relationships, generalizations, use of variables, and unknowns. And to me, these 5 words here can encapsulate a lot of what the heart of algebraic thinking is in that type of response. So let's unpack this further. Well, in one quote that I find helpful, it said, "The language of arithmetic focuses on answers, while the language of algebra focuses on relationships." Well, I think what this is trying to say is that when we think of arithmetic, what we often think of is 2 plus 2 equals 4, or 9 times 8 equals 72. We're very much focused on something and something equals this, and we're focused on getting this. Where algebra goes a step beyond that, of course, and focuses on relationships. It may be as simple as 9 plus something equals 17, but still there's a change in thinking there. Instead of getting a direct computation, we need to think about the relationship between 9 and 17 to think what we need to do to get that unknown number. And there's this extra step of relational thinking that occurs when we are engaged in algebraic thinking and not arithmetic thinking. Another quote to think about says, "Algebraic thinking is about generalizing arithmetic operations and operating on unknown quantities. It involves recognizing and analyzing patterns and developing generalizations about these patterns." Interesting. So here, we may be looking at arithmetic operations, but then trying to go a step further and generalize a rule that's always true for any numbers, and thinking about things like that. And again, we see a lot of those key words in this definition. So what I want you to do is, here are 4 classroom examples. And I'd like you to pause the video and think through each one, maybe even write down whether you think each one, yes, promotes an aspect of algebraic thinking, or no, does not. So pause the video and write those down and then unpause. All right, well, let's see how you did. In number one of this kindergarten class, yes, this would promote several aspects of algebraic thinking, actually. Well, one, obviously, we see the kindergarten class involved in kind of studying patterns here and thinking about different patterns. In this case, there's some physical sound patterns happening. So we see that, but we also see some interesting use of symbols, right, and variables. ABB, ABB. This is a common way for young learners to kind of generalize patterns. Of course, ABB could be stomp, clap, clap, stomp, clap, clap, but maybe that could also represent something like green, yellow, yellow, green, yellow, yellow. And so this use of symbols helps us generalize a pattern to not just stomps and claps, but to lots of things. So there's a lot of algebraic thinking in that example. Number two, let's take a look. Number two, I would argue that no. This is a story problem, but it's more about arithmetic thinking. In this problem, we have John has 4, his mom gave him 7 more. We're really more concerned just about the answer. We just need to think, 4 plus 7 is something, and there's really not much more of an extra step to thinking here than just computing the answer. And number three, again, I'd argue yes on this one because we see, again, a use of a symbol for an unknown that is in a spot that makes us think about the relationship between 7 and 3 and to think about how this relates. I mean, obviously, if you replace the box with an X, it may look more like formal algebra, but this is still kind of solving for that unknown, a use of a symbol. So yes, this has that extra step to go to algebraic thinking. And the last one, number 4, I'd also argue yes. Even though they're just looking at dot figures and growing, this would mean that they're looking at a pattern of figures and trying to then generalize the pattern that's happening to draw the next figures in the sequence, maybe even wondering what the 10th one would look like or how many dots would be in the 100th one. So we could take that and look to study the pattern, articulate the pattern, generalize what that's going to be for the upcoming patterns. And so yes, I'd argue this is a type of algebraic thinking. So let's try 4 more, okay? So here's 4 new ones. Why don't you go ahead and pause the video again and write down yes or no for each one. All right, well, let's see how you did. In number 1, again, I'd argue that yes, even though this is a geometry example, algebraic thinking can still be present in geometry. Because here, this is a type of lesson where students are going around, and typically what this looks like is they have a string or something, and they find different circles in the room, different cylinders, and kind of measure the distance around the circle with the spring, write it down, then measure the distance across the circle or the diameter and write it down. And as they look at different sized circles, they look at patterns, and in that they realize that it seems like the distance around a circle is always about 3 times the length of its diameter. And here we see, again, a looking for patterns and then generalizing, a formula from those patterns. So yes, we see algebraic thinking there. And number 2, we see students making a generalization again, going from 2 specific examples to generalizing, well, I think that's always true. You can take any 2 numbers and add them up and switch them around front to back and back to front, and it's always the same. And in the reading, you may remember that one emphasis was on different properties of mathematics. And here we see the commutative property. And these are definitely algebraic thinking when we ask students to generalize and to see what's always true or sometimes true and to make those types of thinking. In number 3, I'd argue this is no. Although it's good and beneficial to be thinking about what 6 groups of 3 would look like, again, this is just students visualizing what 6 groups of 3 are, working towards a visual computation of the answer. And so it doesn't have that extra step for algebraic thinking. And number 4, number 4, I just realized has a mistake in it. It's missing a number. But let's pretend it said Adam had some airheads. He gave 9 away to his friends. He now has 3. How many did he start with? So I apologize, that one was incorrect there. And if that was the case, I'd argue that yes, this word problem would be algebraic thinking because, again, the unknown is in one of the first 2 numbers, so that there's an extra step of relational thinking where we have to think about the relationship of the numbers to go past it. It's not as simple as just a direct computation. So, all right, well, let's go back to those Common Core standards for a second, operations and algebraic thinking. Well, here's a sample standard that definitely we see algebraic thinking all over it. So let's read it together, but think about this. What grade do you think this occurs in? This standard says use addition and subtraction within 100 to solve 1 and 2 step word problems involving situations of adding to, taking from, putting together, taking apart, and comparing with unknowns in all positions. Example, by using drawings and equations with a symbol for the unknown number to represent the problem. Well, wow, we see lots of those key words there we said earlier. Unknowns, equations, unknown number, lots of things here to think about. Well, what grade level do you think? Well, the answer here is second grade. That 2 right there tells us second grade standard. And the same standard actually occurs at first grade, but it just says within 20. So in first grade, they're still doing the type of algebraic thinking within 1 through 20, and then as they get to second grade, they expand it to 100. So in doing that, you may recall in our past class in CI 430, we had these structures and talked about them: join, separate, part, whole, and compare. And these are the same things talked about in the standard. This is a page from the Common Core Standards in the appendix that kind of just helps teachers understand what it means with variables, with unknowns in all positions, and sample kind of word problems that can fit along that. These are generalized, but these are not the ones you would give students, but give us as teachers a thought here. And as a reminder, we spent time in CI 430 unpacking this and thinking about what that means for young students. Now, recall that, if we turn this into a little story problem, we may have something like this. Kashanda had some grapes for a snack. She gave 7 of them to Grace, and now she has 6 left. How many grapes did she have at the beginning? Well, when doing this, I just want you to recall that the goal here is not to worry about formal algebra at first. We don't need students to write down x plus 7 equals, or x minus 7 equals 6 and tell them to add 7 to both sides. And no. I mean, the goal here is the algebraic thinking is for them to think carefully about, well, what's this problem asking and what makes sense? Start off, we may ask questions about, did Kashanda start with more than 7 grapes or less than 7 grapes? How do we know? And students may want to act this out or use our unifix cubes or other types of manipulatives to act it out, to put it in front of us to think through it. And as teachers, we will model what it looks like, as we figure it out together, we can model what it looks like as an equation with the question mark, minus 7 equals 6, and just trying to get students to realize what the story problem looks like as a math equation when we do that. And that's just the beginning of some good algebraic thinking here in those early grades. Well, let's go back to that helpful definition by Kathy Seeley. And what we're going to do is unpack a few of these different parts of her definition one by one, just to paint a little picture around this. So let's revisit that helpful definition by Kathy Seeley. And what we're going to do is unpack several of the parts of her definition and give some more examples and think through what these actually mean in practice. So let's start with recognizing and analyzing patterns. Well, to begin, in young grades, patterns can look like a lot of things. And here we see some examples with different shapes and figures to go through. But again, as students look at patterns, often they're asked to think what comes next and to describe the pattern. And as we saw in that earlier kindergarten example, they can also recognize the core patterns. For example, in that first example with the 3D shapes, we see a cube, cylinder, prism, cube, cylinder, prism. So that would be called an ABC pattern because it repeats 3 things in sequence over and over again. ABC, ABC, ABC. And again, in doing that, we're using symbols meaningfully and we're generalizing. And we could ask students to create other ABC patterns using other types of objects or sounds or anything. If you look down to the second one there, we see a pattern. And this one incorporates 2 symbols, to the straight up and down, the vertical line, the horizontal line. We call this would be like an AAB sequence, AAB, AAB, AAB. So it would just be called an AAB sequence going through. And again, students will think of what comes next, describe the pattern orally, sometimes start to transition to describing it using the letter symbols and generalizing to other things. These are all examples of repeating patterns. They just repeat over and over and over again. Well, repeating patterns aren't the only types of patterns. We also have growing patterns. Let's take a look at one of those. For example, we might take a look at an initial first step of a pattern where we have those 4 blocks there you see in step 1, and maybe the next step comes in and then it looks like that. So it grew in some way. And we could take a look again in the next one, and it grew again. So this is a pattern, but it's different than the repeating pattern in the sense that we see something changing here a little bit in a different way. Like if we described it, we might say, well, it looks like there is one square being added to the top of the T each time, and two squares being added to the stem of the T each time. And saying this, we have a new type of pattern that keeps going on here. And with this, we could again think about students to think what the next step would look like, to describe the step orally, and again to challenge them. They might think about questions about what would the 10th step look like, or even the 100th step. That forces us to generalize, to think through, and in later grades, and well, just at some grades, we can start thinking about it in terms of variables and equations as well. If we call the step number n, can we think about like, well, the top part of the T is always 2 more than the step number, so it's n plus 2. Oh, interesting. And it looks like the branch of the T coming down is always well, that one's going to be a little more tricky, so I'll have to think about that one. But we can generalize that to go through. So again, patterns can be repeating patterns or growing patterns, and patterns can just be all over the place. It doesn't have to be shapes. Just anything we're doing, a lot of times we can ask students to look for patterns. 100 chart's a good example. There's all sorts of interesting patterns that are in the hundreds chart. If we look at what happens to numbers that are diagonal from each other, or numbers that are 2 apart from each other, or thinking of that. And when you start getting in some geometry like this down here, here's a little cross on the bottom. And here's an interesting pattern. Can you add up the top and bottom of the cross, the 23 and 3? Can you add those up for me? And then add up the left and right side of the cross. What'd you get? Did you get 26 for each of those? Oh, that's interesting. So you got 26 in the top 2 and 26 for the right 2. How does that relate to the middle one, to the 13? Let's look at one more. How about this one? If you add the north and the south, top and bottom, what do you get? Left and right, what do you get? They each were 58 again, And how does that relate to the middle number? Oh, interesting. So if you do that, you can see there's some patterns here. I wonder if that's always true. Can we explore some other ones? Can we talk about, what exists in that pattern and why that is true? These are the types of questions that get algebraic thinking. And so there's lots of types of patterns, and patterns can even be if we're exploring arithmetic and looking at things like 1 plus 3 and 3 plus 1, 2 plus 4 and 4 plus 2, and just realizing that as we do different arithmetic, we notice there's a pattern in our examples, that it doesn't seem to matter what the answer is. So again, patterns are all around us, and as teachers, the more we emphasize what patterns do you see? Do we notice in relationships? Those are questions you want to ask if you're promoting algebraic thinking. The next thing Kathy Seeley says is studying and representing relationships. And I made the asterisk here that often has a focus on variables or meaningful use of symbols and solving for unknowns. So let's talk about that a little bit more. All right? So one symbol we've talked about before, just a quick revisit, is the all-important symbol of the equal sign. I mean, that is a symbol, and understanding that it deeply is very important in mathematics. And we learned last semester that a misconception with the equal sign is called an operational view, that it does something. That kids who would look at this top question here would look at it and say 8 plus 4 equals, and they would put 12 there, because they just think they're supposed to. That after the equal sign, you always put the answer, that it makes an answer. But we know that's not really what the equal sign means. A correct understanding of the equal sign is a relational view of the equal sign, that the left side of the equal sign has to be the same amount as the right side. And that language, again, can be very helpful. The same as, the same amount as, and stressing that can be helpful. That 8 plus 4 has to be the same amount as something plus 5. So if the left side is 12, what would be the number that's missing there to make the right side equal to 12? So it takes away, that language takes away the incorrect view that equal sign makes something or does something, or the answer always comes after the equal sign. And of course, we always talk about things like seeing it as a balance, and there's visuals and manipulatives for that, to think of the left side and the right side of a balance and trying to make the two sides balanced or equal to one another. And again, even questions like the one I have here, but having students from young grades get used to open math sentences is important. When they only see questions again and again, like 8 plus 4 equals something, 2 plus 5 equals something, it creates this incorrect view that, again, the answer always comes after the equal sign. So even at young grades, we can move things around. Something equals 8 plus 4, or like this one here, 8 plus 4 equals something plus 5. And just through conversation and using good language as teachers and modeling, they can develop a good conceptual understanding of the equal sign. Another good strategy is true-false type questions, and these are real engaging. Students enjoy true-false challenges. Well, putting on the board, and like the one in the example there, and to ask students, is this equation true or false? And again, it's a little math talk, but they have to look at it and talk about it and understand that the left side is 9, the right side's 11. They're different, so it's false. That is not what the equal sign is supposed to mean. That would be a false equation. And true-false can be a great way to discuss things. Well, in terms of meaningful use of symbols, we've already seen a little bit of this, but we see that variables don't need to be only boxes and letters, but across the grades, you'll see a lot of creative uses of variables, from fun objects and different pictures that just get students thinking about unknowns, and it turns it more into a puzzle situation and some really good relational thinking. These examples of these puzzles are posted on Moodle, and I encourage you to download them and give them a shot and try some just to have some fun with some algebraic thinking puzzles as they go through. Now, in those last puzzles here, if you try these, all of these variables represent a single number, right? Like the Pikachu equals a certain number. The green lizard is a certain number. And that's a certain way of thinking of a variable. It stands for a constant, a single number. But even at young grades, students get introduced to other kinds of variables that vary. Let's look at what I mean. So in this word problem, Nimra has a tree by her house that has 2 different bird nests in it. One nest is for robins and the other is for cardinals. This morning, she counted 10 total birds in the tree. How many of each type of bird might there have been in the tree? Well, if you think about it, there is not one answer to this question, right? You could have 1 robin and 9 cardinals, or 5 robins and 5 cardinals. There's lots of possibilities here. And that's the point of the problem, that there could be lots of possibilities, but this is an example where if we think about it, a good challenge for students is to think of all the combinations that could go through, and we see a little visual of that on the right side. But again, don't be afraid, we can make connections here that, if R is the number of robins and C is the number of cardinals, that together those would have to equal 10. That's what our visual says. So the equation there would be R plus C equals 10, but here we see an example of variables that vary. These numbers can change depending on the birds and the trees. So this is a good example of variables that vary. Now, in thinking of just relationships and variables and classroom things, I'd like to think about, again, a neat way to bring in even children's literature that can help engage in these types of thinking. So what I'd like you to do now is to pause this video and to type in the link below, it'll bring up a YouTube video of someone reading just a book called 2 of Everything. And go ahead and do that now. Please pause the video and watch the short YouTube reading of this book, and then come back and we'll continue. All right, interesting little story, huh? Well, let's take a look at think about this book. There's lots of things we could do with this book, like a lot of books. I mean, we can read it, but what can we do with it? How can we bring some math out of it and to think about it? What types of math are in this book? What grade levels might be targeted? What do you think some ideas would be that we could do with this book? Well, let's take a look at what some other people have done with this book. Well, so one, we see some classroom examples where people are looking at, there's kind of a general rule for this pot. And students were encouraged to make up different examples. I put, 5 in the pot and 5 came out. 5 plus 5 equals 10. And there's a pattern here, right? And we're generalizing that pattern of seeing what happens in the pot each time to go through. We see just some examples of what some students did with this here. They looked at their own examples and, put these together and looked at patterns and generalized. This is a good way to practice doubles addition here to go through that. But again, we're looking at a rule for the pot. There's a rule there, a generalized rule, and now we're using that rule to make some examples. Well, it's kind of like algebra, isn't it? We have a certain rule or formula, right? And we're using that to make examples. And we could take this to different grade levels as well. If we move from words to symbols, we can see that below. Like we, again, can look at the table at the bottom. I put one thing, and so here, for example, whatever goes in gets multiplied by 2. And so again, as teachers, just get used to the idea that, well, after we start with specific examples, we can generalize those. How could we represent those words with mathematics? So if we say n can be whatever goes in, and then the rule could be times 2, so n times 2. But again, we started with examples, then we talked about it in words, and then we moved towards the symbols. That's going from concrete to abstract, like we've talked about many times in math education. The fun thing is with this is we could, down below, have a pot. You could imagine this pot having many different rules. For example, down below shows a different pot. You put one thing in Mr. Hong's pot and 3 things come out. You put 3 things in and 5 things come out. Interesting. Well, in this one, it's a different pot. So we might think about with words, whatever you put in, you get 2 more things out. So again, as we move towards variables, well, let's call what we put in n. So we get out would have to be that number plus 2. Okay, so you can see moving again from specifics to variables here. And so it's kind of fun to think about representing relationships in different ways as we go through. Again, students can look at different examples, try and describe the rule for the pots in words, and be able to, get used to that idea. And so, again, a book like this can be a context for a lot of good discussion around it. And some teachers with this have had some fun to make little projects, right? They had the students, again, from this book, imagine they found a pot, and they got to come up with their own rule for the pot. And they could make their rules simple or more complicated, or you could tell them it could be a 1-step rule or 2-step rule, and to give their own table there to show what would happen, an in-out table. And now we're actually linking to the idea of functions in math as well. And this is kind of fun. And another teacher, just examples online, is they had teachers do this, and they made a bulletin board, and the students put up a little picture of a pot and put their in and out table on the pot. But if you notice, they didn't put their rule on it. So the fun thing was the other students were given a sheet where they had to look at a pot number and try and figure out the rule. And it became a fun little activity where the students had to try and guess the rule of their peers' pots to go through and to try and make that work. And again, what great looking for patterns and generalizing, looking at relationships. Wow, there's a lot of algebraic thinking going on there in this example. All right, so one last one. We've already talked about this a lot. We just did generalizations in the last one. Students were generalizing patterns from examples, but let's unpack that a bit more. So in generalizing, again, if we have to give a definition to that, one thing we may say is forming a conclusion that's not dependent on the specific numbers involved. Generalizing does not need to involve symbols, but it is an important conclusion for older students. Again, we're making a conclusion that's not dependent on the specific numbers involved. So again, at a young grade, we have students start often with patterns. Have them find 2 groups of 5, and then challenge them to find 5 groups of 2. What do they notice? Oh, it's the same. Do you think that's always the true? Why is that? Well, let's try other examples and see it. 3 groups of 6, 6 groups of 3. It's the same. So again, we generalize. We realize the numbers we put in doesn't matter. As long as you take any 2 numbers and switch them around, it always ends up being the same thing. Interesting. So again, we've generalized a rule here about really multiplication, but in this case, groups of thinking. And again, as our book did, we can use this a lot with properties in mathematics. Look at these for example, and we could have students explore these and look to generalize. This is an example of having them explore the associative property. You're going to notice that in the first example, those end up being equal. And the second example, they end up being equal. And we could test those with different numbers and to realize, again, the order doesn't matter. That the place of the parentheses doesn't matter in terms of order of the operations. We get the same answer either way. But when we try it with division, interesting, the top one would be 2 divided by 2, or 1. And the bottom one would be 12 divided by 3, which is 4. They weren't equal. Interesting. We could try a couple other examples, but so the associative property seems to work with addition and multiplication, but not with division. And again, we're just by looking at examples with numbers, we generalize to a rule that's not dependent on the actual numbers. All right, and again, this can look like so many things. We could have our calculators out and have students exploring patterns with calculators. Dividing by 10, powers of 10 would be important. But imagine students just typing things like this in their calculator, writing down what they get, and then asking them, what patterns do you see? Let's try and generalize. Like, how does it relate? Like in this one, we may notice that every time we divide by a power of 10, well, the decimal's moving to the left. Good. How many spaces to the left is it moving? The same number of spaces as zeros were in our power of 10. Wow, cool. So I think we could try something like 87 divided by 100,000. What would that be? Would it work for 55 divided by 1,000? So again, by starting with patterns, talking about it in words, and then generalizing, we can form rules that are not dependent on those numbers. And you did this a lot with your hallway problem that you looked at with the doors. I mean, you basically were looking at a subset of doors and looking for patterns and trying to generalize what was always true. And you may have remembered that you came to the idea that all perfect square numbers would always be open, and came up with a rule about that well, all perfect square numbers have an odd number of factors because one of their factors is times itself. So it's only counted once. So every number out there has an even number of factors except the perfect squares that have an odd number of factors. And that's why in a problem like this, they were always open. So again, it's just patterns to generalizations. We see that in a classroom that's stressing algebraic thinking and is stressing generalization. There's just kind of questions you'll hear. And you can imagine yourself using some questions like this. Hey, can we find a pattern in these? Can we find a rule that works? Is this true for all numbers? Can we use this idea on other examples? When will that idea work? Can you think of a time when that idea wouldn't work? How can we represent this idea as a formula? What do you notice in all these examples? How are all these examples alike? These kinds of words, just questions, just focus on that algebraic thinking. And I encourage you just to, again, in your repertoire of questions in your toolbox, again, add these in. Talk about patterns and relationships across the grades. It's going to be a powerful way to really ramp up your math discussions. So as we close this off, hopefully this video just helped formalize the idea for you of algebraic thinking, and as a teacher, just get a little better sense of what this looks like across the grades and those key things that entails. And again, as we saw, think about patterns, relationships, generalizations, variables, unknowns. And I think that the heart of that, if we talk about those things, then we're on the right track. So, all right, thanks for being with me on the video, and we'll see you soon. Bye-bye.